Good day. For those of you who do not know us, we're the instructional staff for ECE 150, Professors Hiran Patel and Werner Dietl, and Douglas Harder. In this topic, we're going to discuss classes, arrays, and dynamic allocation. So in this lesson, we will review how arrays of int are initialized. We will then look at how to initialize an array of objects. We will then look at when the constructor and the destructor are called. We will see how to dynamically allocate an instance of a class and again understand when the constructor and destructor are called. We will see how to dynamically allocate an array of instances of a class. We will learn how to call member functions and access member variables on pointers to objects using the arrow operator, and we will learn some more basic subtleties of pointers and objects throughout this talk. Now, to begin, I'd like to review the initialization of local arrays. So, for example, here I've declared a local array of capacity of 5, and each entry will be set to the default value. In this case, of the 5 values, the first 2 will be initialized with 17 and 35. The rest will be initialized to their default value. In this case, each of the entries of the array will be set to their default value. Now, consider this class. It's a rather boring class, but it's here to make a point on how constructors are called for the next example. We have 2 constructors, one that takes a double with a default value, and another that takes 2 integers, the second with a default value. Now, all these constructors are going to do is indicate which constructor was called. So, all right, let's take a look. Here's an example. Here we have an array of C of capacity 10. We have initial values for the first 4 entries of this array. Each of these are passed to the appropriate constructor. Now, the first one is a single integer. Now, the compiler could convert this integer to a double, or it could call the constructor that takes 2 integers, the second with a default value. Well, it sort of makes sense to do less work, and that is to call the constructor with 2 values, the second having a default value of 0. The second calls the constructor with no arguments. Well, the only constructor that can be called with no arguments is the one with a double, where the one parameter has a default value of 0. So the second entry of the array would be initialized by the constructor with a double. The third one, well, there's only one constructor that takes 2 integers, and the fourth one, again, there's only one constructor that takes a single double precision floating point number. The compiler figures these out, and the rest of the entries of the array are initialized with calls to the constructor with 0 arguments. And of course, that would call the constructor that has a single double as an argument, as a parameter with a default value. We can now call the member functions on the entries of this array. And since all of them have been instantiated and initialized, everything is good. Now, if the constructor does not have a constructor that takes no arguments, you must actually provide all arguments for all entries of the array. So here we have a class D that has a single constructor, and the one parameter does not have a default value. So here we have an array of capacity 5, and because there is no constructor that takes 0 arguments, we must provide 5 initial values. All right, so here we do have 5 initial values, so the constructor will be called 5 times, once for each entry of that array with the corresponding initial value passed as an argument. Then we can walk through the array and once again call about on each of those entries, and all is good. Now, when a local array goes out of scope, the destructor is called on each entry of the array, and this is done by the compiler. So here we have, again, a very simple class that only has a single destructor, and that destructor simply indicates that it has been called. Consequently, inside the main function at the bottom, we have an array of capacity 5, just to indicate that nothing happens until the end of the function. We're going to print hello world, and then we will end the function main, in which case the array will go out of scope. Once that array is going out of scope, we will call the destructor 5 times, as expected. Now, given a function, if a parameter of that function is declared to be passed by value, when that function is called, the copy constructor is called to initialize that parameter, making it a copy of the argument. Additionally, when the function returns and that parameter consequently goes out of scope, the destructor is called on that parameter. On the other hand, if a parameter is declared to be passed by reference, when that function is called, again, the parameter is an alias for that argument. So any change to that parameter inside the function will actually be a change to the argument. This is why very often we will pass by constant reference, because we don't want to deal with copying the object, so therefore we pass by reference, but we don't want the function changing the instance, so we pass it by constant reference. Of course, when the function is returned, there's no need to call the destructor, because only the reference variable, that is the alias, goes out of scope. All right, here is a class F, and it has a constructor with no arguments, a copy constructor, and a destructor. And we will see when each of these is called when a function is called. Now, in each of these cases, all it does is indicate that the corresponding constructor or destructor was called. Let's use this function now that has a constructor, copy constructor, and destructor. On the very first line, we declare object to be an instance of F, and consequently the constructor is called. Next, we're going to print to the screen the fact that we will now be calling a pass by reference function. All right, that's just letting us know where we are. Now, when the object is passed by reference to the function by reference, the parameter ref_param is simply an alias for the object inside the body of the function. So any change to ref_param inside the function will actually change the object we declared inside main. So that is simply a reference variable, and when that function exits, that reference variable goes out of scope. Now we're back in the main function, and now we print pass by value. So no calls to the constructor or the destructor or copy constructor were made when ref_param or when object was passed by reference. However, now that the object is being passed by value, the parameter param is initialized with a call to the copy constructor, where the original is the object that is the argument. So now inside the function by value, param is a copy of object, and any changes to param does not affect the original object which was referred to. However, since we've created a new copy of f inside the function by value, when that function exits, we have to call the destructor on that param copy. All right, so that call to this destructor is the destructor of the copy. Now we return to main. We're going to indicate that we are returning from main, and that will call the destructor on the object, or the local variable object that was declared at the front of the class. Now, suppose you have a function that takes an array of objects. What's going to happen here? Well, you'll remember from before, the array is passed just like any other array we've previously seen. It's only the address of the array that is passed to the function. Consequently, if that's all that's being passed, there will not be any calls to any constructors or destructors. In the function, array is just an array pointer, and when the function exits, that particular parameter goes out of scope, but it was only an address. So there's no need to call a destructor. Of course, inside the function byArray, any change to any of the entries of the array will actually change the original objects that are in that array. Just to demonstrate that this works, here is a class that takes a constructor which will store a single integer internally as a private member variable. The member function retrieve will return that particular value. Also, both the constructor, the copy constructor, and the destructor will print a statement to the console output indicating that they are being called. Now, this class G has a constructor that requires one argument. Consequently, if we wanted to declare an array of capacity 5 storing instances of this class, we must initialize all 5 entries. So the first statement declares data to be an array of capacity 5, and the constructor is called 5 times, once for each of the 5 entries of the array. Now, next we call data, or print. We pass data, and all that does is passes that address to the print function. All right, not a problem. It's just an address. So there's no need for a copy constructor or anything else. We're just passing the address of the array into the print function. The print function then steps through the array and calls the retrieve function for each to print them to the screen. So the for loop in the print function then prints the 5 retrieved values. The function print then returns. The parameter array goes out of scope, but the parameter array was simply the address of an array, so no need for a destructor. The same with capacity. Capacity goes out of scope. Back in the original function, the main function now is about to return, so the compiler schedules 5 calls to the destructor. And so the destructor is called on each of the 5 entries of the array. Now, what we haven't discussed yet is the dynamic allocation of objects. It works just like you would expect. For example, the first one here, new int with empty braces, requests memory for sufficient memory for an integer from the operating system, and that memory is initialized with the default value of an int, which is 0. In the second case, we request 4 bytes from the operating system, and that memory is initialized with the value 42. It works the same way with a class. If you call new class name with values for initialization within the braces, you are creating a single instance of this class. And what will happen is the compiler will schedule a call with whatever you passed for initializations as arguments for the constructor. So this call to new first gets sufficient memory from the operating system for an instance of this class. The compiler then schedules a call to the constructor with the arguments you passed. At this point, once the constructor returns, then new returns the address of that new item. The compiler will, of course, decide which constructor you meant to call based on the type of the initial values you pass. If, of course, there are no constructors that take 0 arguments, you must pass the minimal number of required arguments. Now, when you call delete on an object, the compiler schedules a call to the destructor. Once you've called delete, the compiler schedules the call. You never explicitly call the destructor on any object. This is done by the compiler after you call delete on that address. If you forget to call delete, the memory is not deallocated and the destructor is never called. Now, using our last class G, which we previously defined, where we have a constructor that takes exactly 1 argument, a copy constructor and a destructor and a retrieve member function. Here in this function, we declare pointer to item to be a local variable that stores an address. Specifically, it stores the address of an instance of the class G. Now, this pointer is initialized with whatever address is returned by the call to new. New makes a request for sufficient memory to store an instance of G. The operating system returns that memory. The compiler then calls the constructor on that memory location with the argument 3. The object is initialized and the address is then returned and p_item is initialized with that value. So there is our call to the constructor. Next, immediately we call delete on p_item. So this results in a call to the destructor, again scheduled by the compiler. The compiler first calls the destructor on that memory location, and once the destructor returns, then the operating system is given the memory back. And just to be safe, we set p_item to be null pointer. At this point, the main function returns. There is no subsequent call to the destructor because p_item is just a local variable that stores an address. So it will go out of scope and that will be it. Once again, using our class G, here we declare a_item to be a pointer to an instance of G. But now we will assign to a_item memory for an array of 3 instances of G. So when the compiler sees this, the compiler will schedule a call to the operating system requesting sufficient memory for 3 instances of G. The compiler will then schedule 3 separate calls to the constructor. So at index 0, it will call the constructor with the argument 101. At index 1, it will call the constructor with the argument 102. And at index 2, it will call the constructor with the argument 103. When this is finished, new will return the address of the first byte of that block of memory, and that address will be assigned to a_item. Next, when we call delete, the compiler will then schedule 3 separate calls to the destructor, one for each entry of the array, and so all 3 instances of the class G have been cleaned up. We then set a_item to null pointer just so that we don't have a dangling pointer, and when this function returns, the local variable a_item simply goes out of scope. Here, however, we see a mistake. We called new asking for sufficient memory for an array of 3 instances of G. So this resulted in 3 calls to the constructor. However, when we called delete here, we forgot the square brackets, and the compiler now assumes we are only deleting a single instance of an object. This is a problem because what this means is it will only call the destructor on the first entry of the array, the entry at index 0. This could lead to serious issues if there's supposed to be cleanup after every single instance that's declared. For example, you may have memory leaks or other issues that result as a result of not calling the destructor. Now, to access a public member variable or call a public member function on a pointer to an instance of a class, you use the arrow operator and not the dot operator. So for example, using our class G again, the first statement here is a declaration of item as an instance of the class G, and the compiler schedules a call to the constructor with 42 as the argument. Next, we declare pointer to item to be the address of an instance of G, and it is initialized with whatever is returned by the call to new G with the argument 91. This again results in a call to the constructor with the argument 91. This constructor is called on whatever memory was returned by the operating system, and that address is subsequently assigned to the local variable p_item. If we want to now retrieve the value stored in item, we call retrieve with the dot operator, and that returns 42. However, p_item is an address. So an address does not have member variables or member functions. An address is just a number. It's an integer, a 8-byte integer, at least on a 64-bit system. So to tell the compiler to call that member function on the object at that address, we use the arrow operator. So that consequently will print 91. We now call delete on p_item, which calls the destructor on that object at that address, and then we set p_item to null pointer to avoid a dangling pointer. Subsequently, when the function exits, then the compiler sees that item is going out of scope and calls the destructor on item as well. Now, recall with a dynamically allocated array of integers, again, as you can see here, a_items is assigned the address returned. However, when we access the kth entry of a_items, that is the actual integer value there. It is not a pointer. So when we run this, this prints out the values of the three integers. Similarly, if we have a dynamically allocated array of objects, then the index accesses the entry of the array, so on that we have to use the dot operator. So once again, when we call new, this calls the constructor 3 times, once for each entry of the array. Then, if we want to retrieve the item, we access the kth entry of the array, and on that object we call retrieve. So that will retrieve the values 101 through 103. When we call delete on this address, it will call the destructor on each of the 3 entries. And once again, we're finished. We assign a_items, the null pointer, to avoid a dangling pointer, and that local variable goes out of scope. So you can also have an array of pointers. So here, for example, array is declared to have a capacity of 5, but it's an array of 5 pointers to instances of the class G. Now, a pointer is an address. The default value of an address is the null pointer. So by having just empty braces after the declaration, that simply initializes each of the 5 entries of the array to null pointer. There are no calls to the constructor at this point. So right now, there is no output. Now, let's look at this first loop. You notice that k starts at 0, but k is incremented by 2, and it goes until k is less, so long as k is less than 5. So in this case, we can deduce that k will be 0, then 2, then 4. The first time the loop body runs, we make a call to new. So we dynamically allocate memory for one instance of G, and so the operating system gives us 4 bytes. Then the compiler schedules a call to the constructor on that location in memory, and the argument is 100. So the constructor initializes that instance of G with the member variable being assigned 100. New then returns that address, and array index 0 is set or assigned that address. We do not change array 1, so that remains null pointer. Next time the loop runs, k is equal to 2. We dynamically allocate another 4 bytes, call the constructor on that memory with the argument 102, and the returned address is assigned to array index 2. The last time the loop body runs, k is equal to 4, we dynamically request memory from the operating system. It allocates 4 bytes, it calls the constructor on those 4 bytes, and the argument to the constructor is 104, and the returned address is assigned to array entry 4. Now, each of these 3 were called simply with a call to new for one instance. So even though it's an array of pointers, each of the dynamically allocated memories is just a single instance of G. All right, so now let's go through the next loop, which goes through each of the entries of the array. So when k is equal to 0, k0 is no longer the null pointer. So we now want to retrieve call the retrieve member function of the object at that address. So therefore we use the arrow operator. That will print 100 to the screen. The next step is let's deallocate that memory. And so we will call delete passing array 0, the address stored in array 0, and that will call the destructor on that dynamically allocated memory, which will then tell the operating system that that one location in memory is no longer required. We then set array 0 to be null pointer. Now, when k is equal to 1, array 1 is equal to null pointer, so nothing happens. The next time the loop body runs, k is equal to 2. K2 is not equal to the null pointer, so we again request, hey, let's call the retrieve member function on the object stored at the address stored at array 2. That will print 102, and then we delete what is there, and we assign that entry of the array null pointer. Third time it runs, nothing. Fourth time it runs, we print out 104, set the call delete on the fourth entry of the array, set that entry to null pointer, and the loop is finished. Now, when main exits, there is no subsequent call to the destructor because array is simply a local array that happens to be storing 5 addresses. Currently, those 5 addresses are null pointer, but notice, if in the second loop we did not call delete on those 3 dynamically allocated addresses, then there would actually be a memory leak, because while array would go out of scope, we would not yet have returned any of that memory to the operating system. So that would actually be 3 instances of memory leaks. So here's a general rule. If you can print the variable, be it a local variable, a parameter, or a reference to either of these, or an array entry, and printing it produces an address, then use the arrow operator. Otherwise, use the dot operator. Now, it's important to note, if you have not correctly overloaded the appropriate left shift operator for printing an instance of a particular class, printing it may actually cause a compilation error. Fortunately, you can always print an address. That is, if it is a pointer, you can always print it to the screen and you will see some sort of hexadecimal number on the screen. If it's not a hexadecimal number and you haven't done anything fancy, then you should be using the dot operator. So a guideline. If you meticulously follow the naming convention of prefixing pointers with p underscore, this will help you to remember to use the arrow operator when you're calling either a member function or member variable. It will also remind you that when it comes time to clean up that dynamically allocated memory, you must simply use delete. If you prefix any dynamically allocated array with a underscore, then that will help you to remember to use the index, and then on a particular index, use the dot operator to access a member variable or member function. And again, it will also help you to remember to call delete with square brackets on that variable name. Otherwise, you just have a name and you use the dot operator, and you do not call delete because it is a local variable or a parameter. Now, it is possible to have pointers to pointers and pointers to arrays of pointers to pointers to arrays, etc., 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 but that's all way beyond the scope of this course. We will, however, look at one last example. Here's a class that I'm calling node, and it just has 2 public member variables for simplicity. The first is an integer. The second is the address of another instance of this class. That is, it is a pointer to another instance of this class. In fact, it could be a pointer to itself. Let's now use this class. Now, remember that everything in this class is public, so we can initialize the two member variables simply by providing those two values when we call the constructor. So, P42 is a pointer to a node. We call new node and initialize the two member variables with 42 and null pointer. That returns the address. Well, that object appears to be allocated at 13F0A8. So that is the value that is assigned to P42, and we can print that to the screen. Next, we call for a new node that will request enough memory for a node, and the two entries will be initialized now with 91 and the address of P42. So this is the object that is created, and it happens to have been created at address B0-3C50, and that is the value that is printed to the screen. All right, now this next print statement has us print whatever member variable is at the address stored at 91. Specifically the value member variable. So the address P91 is B0-3C50, and at that address value has the value 91, so that's printed to the screen. Okay, next. Now we are printing the value of the member variable pointer to next at the address P91. Once again, the P_next address at the address P91 is 13F0A8, that value that is stored there. So that's what's printed to the screen. Now here's the interesting one. So at the address P91, get the address of the member variable pNext. Now, what is at that address, get the member variable value. Well, the address at pNext of P91 is 13F0A8. So the value at that address is 42. So that's going to print 42 to the screen. Also, the pNext value at the pNext value of P91 is the null pointer. So that's going to print 0. All right, next. I'm going to call delete not on P91, but P91 pointing to pointer to next. Well, the member variable pointer to next at the address of P91, which is B0-3C50, is the address 13F0A8. So that tells the operating system we no longer need the memory at the address 13F0A8. That memory is now deleted. It is gone. We then assign P91 pointing to next null pointer. So that sets the second member variable of that instance to 0, the null pointer. Now, interestingly enough, P42 is still assigned an address. It's assigned the address 13F0A8. But that memory no longer exists. So technically right now, P42 is actually a dangling pointer. Why is this? Because we had one local variable and one member variable that stored that same address. When we deleted one of those, then the other became a dangling pointer. So if we're not careful and set p42 also to null pointer, then we will continue to have a dangling pointer. So we have to set p42 to null pointer as well. Next, we can delete p91. That deletes that object, and we assign p91 to null pointer. At this point, the two local variables p91 and p42 go out of scope, but they're just addresses, so nothing else happens. Now, following this topic, you now know how to initialize arrays of objects, and you know that the initial values are required if no constructor takes 0 arguments. Also, you understand when the constructors and destructors are called. You know how to dynamically allocate and delete objects and arrays of objects. And you have a better understanding, hopefully, of arrays and pointers and how they work. We also gave some tips on how to remember when to use the dot operator and the arrow operator. You've been also introduced to classes that have member variables that are themselves pointers. Here are the references, the colophon, and a disclaimer. Cheers!